No, nobody tried that. Yeah, Vishnu has tried. Yeah, good. Could you solve it, Vishnu? Was there any difficulty?
No, it was easy.
You solved it manually, no, not coded, right?
No, manually, manually.
Okay. Okay. So let us just quickly see that question and then we'll move on. Okay. So this was the question given to you. Okay. So which is there was a training set, data set, where we had so we have 4-dimension data, isn't it? Like we have 4 attributes. Okay, and then we have say some 15, 10, 11. I don't know, 3, 6, 9, 12, 14. I think 14 instances. Okay, and then it's a binary classification problem because we have yes or no as the classes. Okay, and then all the attributes are categoric in this example. Okay, so I'm just explaining how what is your data looking like. Okay, okay, and then just a second. Yeah. So now we are supposed to find predict for a new data sample, which is age less than 30, income equal to medium, student equal to yes, credit rating equal to fair. Okay, and we are supposed to predict whether By's computer is yes or no. That is our question. Okay. Now, how do we do that? We understand that from the previous example, for each attribute given the class, we assume that the attributes are independent of each other, and we try to find those uh, what is that conditional probability, multiply all, and with the prior probability of that class. So like this we find for both the class, and whichever is high, that is what we take as the label for the particular unknown sample. So here we know that the possibility is yes or no. Okay, so we are going to predict probability of yes given x and probability of no given the sample. So for that, we know that we have to write, say, probability of the first, if it is, what is that probability? We are finding the probability of the class being yes, I mean data being yes. We know that we have to find probability of yes into probability of age less than or equal to 30 given yes, into probability of medium given yes, probability of student equal to yes given yes, probability of credit rating equal to fair given yes. Okay, and how do we find that? We have to see a probability of yes, we will find how many yes are there in the total samples. Okay, and then with which, like, how do you find age less than or equal to 30 given yes? In the instances where we have labels as yes, we will count the number of cases where we have age less than or equal to 30. So here if you see probability of yes and no would be 9 by 14, 5 by 14. And say the first example, that is age less than or equal to 30 given yes. That is, we have 9 instances with yes, out of which we have age less than or equal to 30 in only 2 instances. So that is the probability. Okay. So like this we have to find for each attribute. For yes, same way for no also. Now we have to multiply them all together for a particular class. So we get for what is that? For yes we get a value, for no we get a value. Okay, and finally we should see what is the maximum. So here yes has come more, the value is more for yes class, so of course we will choose yes. Okay, so that is how we classify any at new instance to the naive Bayes according to the naive Bayes algorithm. And we also mentioned that our main assumption is, given the class, we assume that the attributes are independent of each other. Attribute means, here what are the attributes? The attributes are age, income, student, credit rating, and the class is Bayes computer, the last one. It need not be always the last one. Don't assume such things, okay? Always we should see what is the problem and what is our class. Based on that, we will make our predictions. So, age, income, student, credit rating, they all are features or attributes. Okay, and then Now we also discussed about the zero probability problem. That is, say for example, we have when we calculate, like say given yes, what is the probability of income equal to low, something like that. Assume that we don't have any instance, okay, in that particular case. So only one conditional probability is actually zero, but then since we are multiplying everything together, the whole term would become zero. Okay, so that is not correct actually. So what we have to do, we have to solve it somehow. So that one usual approach is Laplacian correction. Okay, so for that, or we also say it as smoothing. Okay, so what we do, so here we identify how many value for that particular attribute. So here in this example, we have 3 values for that attribute. So each of the case, we are increasing by 1. Okay, that is how we like it. If suddenly we increase only that particular value, there will be a change in the distribution. So we just increase, we are assuming that we are increasing for all these values of the same of that attribute. So since we have 3 values for this particular attribute called income, we add 3. Okay, and for each we are adding 1. So what happens, previously our probability was 0 by 1000, 990 by 1000, 10 by 1000, whereas after adding 1 it would be 1 by 1003, and 991 by 1003 and 11 by 1003, because we have added 1 on the numerator for each of the case, and since everywhere we have increased 1, the whole number of samples increased by 3. Okay, so there is a small change we are making, but we are assuming that anyway when we take the probability, in this case we are taking probability only. So probability is still approximately 0, but then it is not 0. So we will not get a 0 value for the whole thing. Okay, so that, just to solve that problem. Okay, so now I think this slide we didn't cover last class. So main advantages of name-based classifier. See, for multi-class classification, it is the same approach. We find for all the classes this probability, like we found for yes, no. We will find, say, for example, if it was 3 different groups, okay. Say we have dengue, malaria, and say some other disease, okay. Or say typhoid, okay. So 3 different diseases. So we find the probability of the given instance being typhoid. We find the probability of this being the second and third, and then whichever is maximum we take that. Okay, so usually main advantage is it is easy, it is simple. No, you are also trying, it's very simple, we don't have much calculation. So of course the algorithm is very simple and straightforward. Okay, so implementation is simple, and many cases we get good result, not like always, but then like even in text classification and all, if you see, there are many cases where we have good accuracy with name-based classifier. Even in diagnosis of disease, etc., we have recent performance with this classifier, though it is simple mathematically. Okay, but then disadvantage is, one strong disadvantage is, we are assuming that given the class, the attributes are independent of each other, but actually this may not be the case. There may be dependencies between the attributes. When something is there, a particular value, actually because of that there is some other difference. Okay, something of that sort, like say for example, something like say maybe something like there is a variation in the sugar, and then there is some associated features for that particular patient because he is diabetic. So there are relation between those attributes, which we don't consider in our example, in the sense in our naive base, because that is the assumption what we make actually. So there is some kind of loss in the accuracy. Okay, so practically dependencies exist among the variables, like say hospitals, patients, profile, age, family history, etc. Symptoms, say fever, cough. So when you have fever, I mean when you have cough, there is a high chance that you have fever also. But we might just take it as 2 different attributes. Okay, same way. Okay, so dependencies, we cannot tell that there is no dependency. So sometimes we may have strong dependencies between the attributes, so our model might not be performing well. So there are other things, other modification, that is Bayesian belief networks. As of now we are not covering that, but understand that that can be modeled based on that Bayesian belief network. So, but naive-based classifier will not be able to handle it. Okay. So that's all with that chapter, in the sense that topic. Okay. Let us move on to the next. So I think I mentioned in lab that we'll just cover are my slides visible, students? Can one of you just, yeah.
Yes.
Yes, is it? Okay, thank you. So I was mentioning that I'll just cover model selection and evaluation also, because next week onwards you're trying to do your different algorithms, isn't it? So how do, like, you may apply the algorithm, but then you don't know how to test it, isn't it? So we have learned that there is something like a training testing approach, but then we don't know how to test it or what parameters should be used. So that is why I am bringing this. Usually it comes little end in the sense, like, we usually tell about the algorithms and then we tell how to evaluate, but then it may not make sense if I cover it last, because now you will start, like, you have already learned KNN algorithm and also naive Bayes algorithm. You would be implementing that in your labs. So then you need to compare, etc., isn't it? So what measures you will know, you should know, so that you will know when results come, what are they? Okay. So that's my intention why I'm starting this initially itself. Okay. So what are the evaluation metrics? Okay. Of course, accuracy is one term which we are very familiar. Are there some other metrics also? That's what we are seeing. Okay. And then what are the methods? Like, how do we test? Is it just some samples belonging to a group are made for training and then some are falling for testing, etc.? Or are there other methods? So that we are going to check. And how do we compare? So all that. Okay. So what are the metrics basically? That is what initially we are seeing. So first of all, this is very, very important. I know that I understand that many are very familiar with this term, but assuming that there are few who have not taken any machine learning related courses, or you have forgotten, I am just telling from the basic. Okay. So kindly excuse if it is very simple. So what is this confusion matrix? Okay. So we have something called true positive, false negative, true negative. Don't take it like just some terms or where it falls in that matrix, etc. Understand what it is first, and then only you take, because if you know what are these four things, all other metrics are just based on the formula. So you should be able to identify these four things from the given data. Okay. So assuming that, say for example, you remember that Bayes theorem question, no? So we have cancer, the patient has cancer, and the model is testing it as positive or negative. Okay. So um, when I say true positive, that is, the patient actually has cancer and the model also predicted that he is having cancer. So then that is, it is positive and that is predicted correctly by the model. So true positive. Okay. So that is true positive from the model side. Okay. So when we say true positive, model has predicted it as positive and it is correct. That is the way you should think to recollect it properly. So true positive. Now what is true negative? So the model has predicted that he does not have cancer and that prediction is correct. Which means what? Actually the patient does not have cancer. Okay. And the model also said the same. Okay. So true negative, that is the term what we use. So the model has predicted, assuming that cancer positive, negative, that's what we are going to, just relating to an example. So true negative means the cancer is negative actually, and the model also predicted it as negative. So prediction is negative and that prediction is correct. Okay. So that is true negative. Now what could be false positive? Can somebody say? What is false positive then?
It is predicted as positive, but
Yeah.
it is actually negative.
Yeah, so it is predicted, the model predicted it to be positive, but then it's a false prediction or it's a wrong prediction. Okay, which means The model has predicted it as positive, and it is wrong means what? Actually, it was negative, but the model predicted as positive. Okay. Actually, there was no cancer, but the model predicted it as positive. So it's a false positive. Now, false negative means the same way. The model predicted as negative, no cancer, but actually it is wrong. So the prediction is wrong. That is that false in denoting. Okay. So false negative means model predicted as negative and the prediction is wrong. So true means the prediction is correct. False means the prediction is wrong. That way you can relate. Don't get confused with that term. Okay, so this true positive, false positive, true negative, false negative are very, very important. Okay, based on which you will actually follow all the other metrics. Now, in the next example, what is shown below, we have a confusion matrix. Okay, just a second. There is a confusion matrix. Okay, sorry. We have a class like previous example, boys computer is equal to yes, boys computer equal to no. That is our class. Okay, and it is mentioned actual class on the left side and predicted class on the right side. So which means our predicted class would be our what is that? On the top of the row, the first row, what you see, equal to yes, equal to no, that is our prediction, and actual class is our first column. Okay, that is our Bayes computer equal to actually yes, Bayes computer equal to actually no. Of course, we will not have any issue in relating our what is that, true positive to negative, because that is always that diagonal part. So 6954 is our true positive, 2588 is our true negative. Okay, since we have the same mapping there just above, we may not have a confusion. Otherwise, also you should know how to understand. So here it is mentioned that actual class, like what is 412? How do we know whether it's false positive or false negative? So actual class is no, but the model has predicted it as yes. That's what is our 412. So which means yes is the prediction made, but that is a wrong prediction. So it's a false positive. Okay. And if it is 46, okay, so there also we have no as a prediction by the model, whereas it was actually yes. So it is a false negative. Okay, this is how you will actually understand that. Okay, so the model predicted altogether 7366 as yes, and the model predicted total 2634 as no. Okay, that's how we have to identify. Same way, actually in the data set, we had 7000 as the class yes and 3000 as the class no. Okay, this is how we get the total things in our confusion matrix. Okay, then basically we'll identify true positive, true negative, false positive. But we need to even just identify those sums just to understand. Okay, so this is how our confusion matrix is. Now, based on this, what? Yeah. So, whether I write it as true positive, true negative or not, anyway we have this actual class, predicted class. So we should be able to identify. Anyway, it is written below also. True positive, true negative, false positive, false negative. Okay. Now, accuracy is true positive plus true negative by the all four terms. Okay. That is actually the whole data. Okay. So A plus B plus C plus D, the whole total sum. Okay. And on the numerator, what do we have? True positive and true negative. That means correct predictions made by the model. Okay. Because true positive, true negative out of the total samples. Okay. That is our accuracy. Okay. Usually what we feel accuracy is one good metric, isn't it? Because we are telling how much well the model has predicted. But do you feel or have you read about accuracy not being always so correct, or there are issues with accuracy? Anyone? Any one of you, have you heard of accuracy not being the best always, or any issues with always just going behind accuracy? Can you just suggest? One of you unmute and say me something just to know your presence. Let it be wrong. I am still happy if you respond.
No, it's not always correct.
Yeah,
Accuracy.
but do you
Ma'am,
see? Yeah,
imbalanced data. Like when
yeah,
you have
imbalanced data. So can you tell me? I can't see your names. So can you
look
just tell me, Lokesh? So can you tell me, Lokesh, what is imbalance in the data?
like when you have two set of data, when you have one particular data having like high
Two
like
classes. That is where
yes
you have imbalance. Okay. One class has lot of data and then the
yes
other class has very minimal data, isn't it?
yes
So say for example, we have 10,000 data. Okay. And in that, assume that, like say, if it was cancer and no cancer. If you take 10,000 patient details, we may have only 10 patients with cancer. That is how actually our data is, isn't it? We may not have like 1,000 people with cancer. So when you take example of 10,000 people, you may have only 10 people with a particular cancer if you're doing an analysis of cancer. Okay. So we have 9990 samples, okay, 9,990 samples who are not having cancer, whereas we have only 10 samples with cancer. So what happens here? If you find out the accuracy, okay, our true negative is less, but then all other, our true positive is so high, okay. Because of that, our accuracy will be very high. But are we doing it right? What is happening? I'll just show that example. It is not here. I think I removed it somewhere. Just a second. Okay. Anyway, I think I have removed it or something has happened. It's okay. Assume that, like, say, let me just type it then. Okay. Did I skip it somewhere? No. Okay, leave it. I'll just type it. So assume that we have, say, something like just a second. You're able to still see my screen, right? So we have, say, 9990 as positive. I mean, in the sense, yeah, cancer negative actually. Okay. And we have, say, 10 samples which are positive, or say cancer and no cancer. Okay. If this is the case in our data sample, actually there is, in this data, it is highly imbalanced. We have only we have two classes here. No cancer is 9990, and then we have only 10 where we have cancer. So, I mean, the patients have cancer. So, in our class, if you consider, one class is having lot of data and the other class is minority, we say. There is an imbalance. Okay. So, what happens here is, yeah. So what happens here is, now if you see this true positive, true negative, actually your model might have predicted this wrong. Okay. This 10 is not, 10 is also predicted as, assume this 10 is also predicted as, by your model as, what is that? No cancer. Okay. By the model. Okay. And the first two are the actual situation and the rest is the model prediction. Okay, model prediction. So what happens here? 10, okay, whole 1,000, assume that everything is predicted, whole 10,000, okay, is predicted as not C by the model. If that is the case, how do we calculate the accuracy? Can you tell me what would be accuracy value? So this is our formula, okay. Can somebody tell me how do we calculate accuracy in this case? We know that true positive plus true negative by all, isn't it? Our accuracy is. So how do we calculate in this case? Our model prediction, we know what is true positive, true negative. Can somebody say me? True positive is 0, isn't it? The model has not predicted anything as positive. Positive in the sense, assume that positive means cancerous and negative means no cancer. So here we don't have anything as true positive, okay? And what is true negative? How much correctly it is predicted? So 9990 are correct, isn't it? These are the correct prediction. But what is our denominator? It is the whole sample, so it is 10,000. Isn't it? So this is how, like, everything together, like all the 4 together in our confusion matrix, if you add, it is the whole data. So now, if you find this value, it is very high value, isn't it? Like if you see, what is the value for this? What is the value you get? Am I forgetting 10 or I am correct? Correct only, no? 9,990. Okay. So if you try to figure out, the value is very high because we have only like huge huge number of one sample, one class, okay, and that is actually predicted correctly by our model, okay. So since our other class, which is our cancerous class, is only having 10 samples, okay, though it is actually fully mispredicted, but since the other class is very high, our correct prediction is actually misleading, okay, and we'll get a good accuracy value. So this is why we have an issue when you just stick on to accuracy value, okay. Is that fine? Is that making more sense? Why we should not always stick on to just accuracy? One basic case is your data has an imbalance in your data, okay. So any doubt in that? Okay. You all are parallelly attending the presentation of your company also? I don't know. Okay. So whenever you have a, if you see in this particular case of cancer, here actually you are predicting them as no cancer. Then actually the patients were having cancer, which is actually very dangerous, isn't it? So specifically when you are having that minority class, which is very important, surely if you bother just about accuracy, it is surely going to fail. Your model might fail, okay, because your model is predicting them as no cancer, where actually the patients were having cancer, okay, which is actually very critical in this case. Because see the other case, like if there were true negatives, false negatives, what happens? False negative means false positives, okay. False negatives are very critical here. That means you are telling there is no cancer, but the patient actually has cancer in this particular domain, that is medical domain, or having a disease or not. So you are predicting that the patient not having a cancer where actually the patient has. So what happens is, assume the actual scenario. Say you have given a model, because your accuracy is very good, you have given to the hospital, and when a patient, or maybe not hospital, maybe it's a online available tool or something where people install it in their phone. So then what happens when there are some particular features and your model predicts as no cancer? What happens actually, that person might be having cancer and your model is going to predict it as no cancer. It might be misleading. They may not take treatment, isn't it? Whereas the other false prediction, that is, the model is predicting it as positive, false positive in this case, that is, a model is predicting as positive, but actually the person is not having cancer. It is still little better, because though they would panic, they will still go and do other tests, and then they will get to know that it is not cancer, okay. So in certain cases, certain false predictions are having more weightage, okay. It's not like you can just have a little bit of miscorrect predictions. So that is also contributing, okay. So in this case, actually, when it's a by computer, yes or no, maybe it's not so critical, or when it is spam or ham, maybe it's not so critical. But then when you say about a cancer patient, misleading him that he is not having cancer is very, very critical. So very, very incorrect. So there actually this is very your model actually fails. So that is why accuracy is not at all like always like one kind of metric which we'll choose. We have all other sorts of metrics. Okay, so this is what they are saying. So we have our true positive, false negative, false positive, true negative. Okay, and how we are finding accuracy, that is our true positive plus true negative by all. Error rate is 1 minus accuracy. And then why we are going to this sensitivity, specificity and all, that's what we are telling, class imbalance problem. We'll see, we may not see algorithms, but you should understand that there are cases how to handle this class imbalance also. That is, say, whenever what is class imbalance problem? When we talk about, say, two class problem, say we have cancer positive, negative, where we have one class very less, like we saw the previous example, and the other class have large number of samples. Okay, so that is a class imbalance problem. Many of your algorithms may not work well. So usually we handle the class imbalance problem and then give our data to the model. Okay, significant majority of one class. Okay, so we usually say majority class and minority class. It can be either ways. It need not be always negative class, minority would be positive class, etc. Okay, so they are talking about the fraudulent class. So frauds may be very less when you take the whole data, like fraudulent network connection or something like that. So it may be some 10 samples or 20 samples, whereas the other might be 10,000 samples. So you have a highly imbalanced data. Okay, so that is where your models might not predict well. So we'll have a class imbalance handling. That is like, say, a very basic approach would be like, you can remove some samples and make it the majority samples you can decrease. That is one approach, but may not be very sensible always, because, say, for example, we have only a few sample sets, and in that if you again remove some samples, it may not make sense. So there are other ways where we can bring up the minority class. So like very generic, generally used approach is SMOT, we say. It is actually oversampling, undersampling and oversampling. Okay, so oversampling is you are increasing or manually generating or synthesizing, we can say. Okay, synthesizing some samples which are similar to those in minority class. Okay, like, say, you can say something like k-nearest approach, etc. So we find very similar points and we synthesize new points which are very similar to the existing points. Points, when I mean in 2 dimension, we can visualize. That's why I'm saying like that. So each of our vectors which are there in our minority class, we try to generate more, synthesize more of such similar points. Okay, and then increase our minority class, and then we have a prediction. Of course, you may think that we are actually giving some new samples which are actually not existing in our data set. Of course, it is not exactly correct, but then since we are actually generating based on an approach which are like very similar data points which are already there, it may not have major issues. Okay, so that kind of trade-off is there, undersampling or oversampling, etc. We can still see that little later, but there is a class imbalance problem. Okay, and then so when you take a data set, even this is one kind of thing what you will handle. Okay, before giving to the model. So now, after which we understand that accuracy is not always the same, just one metric what we would go with. So we have sensitivity, specificity and all. So sensitivity is true positive by P. What is P? Actual P. Okay, so if you see in the confusion matrix, it is our P is written in that in the leftmost corner. If you see that confusion matrix is available, so if you see P, that is your actual cancer. Okay, the predicted cancer is the first column. The first row is our actual cancer sample. Okay, actual class. Okay, not cancer. I was meaning about the example. So it is actual class. So the total positives, total positive samples or one class of your data. Okay, so that is true positive by positive. Okay, and then that is sensitivity. Specificity is true negative by negative. So if we consider these two, then we'll understand that sensitivity is good, specificity is not good, or sensitivity is good. No, in the sense, in this case of our previous example of cancer data, our positive data, true sensitivity would be bad. So then we'll understand that we are not able to classify one group. So then we understand that there is some issue in our data. So that's why we'll consider other measures also, not just accuracy. Okay. So even precision recall. Okay. So precision is like, say, when we say it is like what percentage of tuples the classifier labeled as positive are actually positive. Okay. So if you say true positive by true positive plus false positive. So what is that? So false positive means actually they were negative. Okay. And uh, true positive means they are actually positive. But then what we are talking is how many were labeled by the model as positive. That is our denominator. Okay. The model has told that many as positive. Okay. Out of which only true positive are the correct ones. That is our precision telling. So when we talk about the denominator in the precision, that is actually number of samples which are predicted by the model as positive. Okay, out of which what is our numerator? That is the correct ones. Okay, so that is our precision. And what is recall? Recall is percentage of positive tuples. What percentage of positive tuples did the classifier label as positive? That is our why is our numerator denominator like this? True positive plus false negative. Positive, of course, we can identify that it is positive. What is false negative? That means the model predicted as negative, but then they were actually positive, isn't it? That's when it got it as false negative. So that is actually the denominator is actual positive cases. Okay, not the predicted ones. Actual positive cases are our denominator in our recall, out of which numerator is our model predicted correctly positive. Okay, so that is the two things. Okay, the perfect score is always 1. So we should see how good our model is based on that. Okay, so we'll also see precision, recall, sensitivity, specificity, etc. And based on that only we'll choose our model. Okay, so there is something like you have a harmonic mean of precision and recall. Some papers and all, if you have seen, you would see that F measure also they use. Okay, so these are all other metrics because accuracy alone would not help us in all the cases. Okay, so there is something called ROC curve also. I think you would have seen here and there or read, etc. So actually it is for, if we plot the ROC curve, actually if you see, it is false positive rate versus true positive rate. So what happens is there are a diagonal line actually, if you see, that is like a baseline, like you should be having the ROC above that. Okay. So maybe we can just tell like 50% accuracy is like obviously should be there, because maybe we can say when you toss a coin, even that would give a 50% chance, isn't it? Like if you guess. So at least that much accuracy should be there, kind of that way. Okay. So our model should be above that. So here actually the line is our baseline, like at least above that. Okay. It's not, it's like a minimum threshold kind of thing, above which your model should be, of course. Okay. And then if you see, there is two curves, isn't it? So there is a curve which is like towards the top, and then there is a curve which is very near to that diagonal line. So which is more good model, can you tell? It is written that area under the ROC curve is the measure of the accuracy of the model. Now, can you tell me which would be the better model? I should have named it, but I have not. Okay. Can somebody say me?
The upper one, ma'am.
The upper one, yeah. So why do you feel so?
Ma'am, area under that curve is more than the
More,
area.
yes, correct. So this, can you see that red, what I have drawn now? Is it visible for you?
Yes, ma'am.
Yeah, so this curve, what we are talking, is the better model than this. Okay, this is this second one. Okay, the small circle what I have drawn, that curve is not the better one. The upper curve is more better because we have more area under the curve. Okay, that's how when we plot two models ROC, we understand which is better. So we plot the ROC for the models and we compare which is better. Okay, so this is also one approach what we take. Okay, So you will actually see when you code in Python and all these comes, okay, all these packages are there. We'll just use it. But then when you get the results, you should be able to interpret. That's why I'm just telling. Okay. So now this is just an example, okay, where cancer is yes is this much, and then we have, so the just what they are concluding is, here also if you see the accuracy is 96%, okay, actually it is very good, we may feel, but then if you see the precision and recall, they are very bad. Sensitivity is too less. So we understand that there is some misclassification going on. Okay, then we'll get into the data and see what is wrong. So that is why we even consider other metrics. Always we may not be analyzing the data sometimes. So even after not seeing the data, if you predict and see the other metrics other than accuracy, we'll get to know that there is something wrong. Our model is not perfect. So we go and check what is wrong and then accordingly. So we'll not stick on to that model because our model is having low sensitivity. It shouldn't be that way. Okay. So we are just telling a perfect precision score of 1 would mean that the classifier every what is that? Every item that the classifier labeled as belonging to the class does indeed belong to the class, that particular class. So same way, but of course we are not talking about the mislabeled one. We are just telling how much percentage of labeled ones are correctly labeled. That's what we are talking about. If you talk about precision, same way recall also. Okay. Now next is actually model selection. Okay, I think it's time. It may not. I won't be able to finish this. This we are talking about. We were like initially, I think in the initial classes, we were talking about what is that? 70-30. I think here I don't remember whether it's the other class. 80-20. Whether it's always the generic approach, whether it's a good approach, etc. People were asking. So you would have seen also that we give the training like 80% of the data for training and 20 or 70% of the data for training, and then remaining 30 we give for testing, and that's how we evaluate the model. So always that is not the approach. We have other approaches like cross validation. So we'll see that in the next class. Do you have anything else to ask or to tell? I think most of you have formed the groups. I'll just